Welcome to SLO6 video 4, where we'll be discussing the reactions of Grignard reagents with nitriles and carboxylic acids. So we'll get started with nitriles first. And we can think about a simple kind of a reaction with the nitrile functional group. So just to remind you, that's a carbon-nitrogen triple bond with a standard set of conditions you'd expect for a Grignard reaction. So some kind of an organometallic nucleophile followed by some kind of a water or aqueous workup. So if we run these reactions, you might, if you look at the nitrile, you might think, oh, well, this carbon here is at the +3 oxidation level because I've got 3 different bonds to nitrogen, which is more electronegative than carbon. And I've seen with esters in the previous video that, like carboxylic acid derivatives, carbon at +3 oxidation states, or levels, excuse me, those do double additions. So I might expect to incorporate 2 different methyl groups, and maybe I would destroy both of the CN pi bonds, right? So I'd end up with like a carbon-nitrogen single bond. But it turns out that that's not what happens. And what happens is actually very surprising. So if we actually looked at experimental data here, we could run the reaction, purify the compound that we made, and we could actually analyze it by proton and carbon NMR. So carbon NMR, we would actually see a signal at about 200 ppm. And by proton NMR, we would see a singlet integrating to 3 relative to the integration of 5 for the phenyl group. So what that tells me is 2 things. The integration values tell me how many methyl groups I have. Just 1, right? 3 protons from 1 methyl group. And the carbon NMR signal at about 200 ppm is also indicative of not any kind of a carbon-nitrogen functional group, but a ketone. So if I take all that evidence together, and if I assume that the aromatic ring that is pH doesn't change, which is fairly reasonable, then I would expect to actually have my phenyl group attached to a carbon where the methyl group is engaged, because remember that carbons of nitriles are electrophilic, then we would end up with a ketone. Weird. So there's a couple of things to observe here. One is that there's a single addition. Nitriles undergo, that's not how you spell undergo at all. Single addition. The other is that we don't even have nitrogen at all anymore. It's gone. So what gives? And moreover, where did the oxygen come from? Well, I'm not sure yet about where the nitrogen went, but if I look carefully at my set of reagents, the only place where I could be gaining oxygen is from the water. That this oxygen is somehow being incorporated into the product, and you can actually figure this out, right? You could use water that has like an oxygen that's a different isotope than normal, like O18, and you could actually use that as your workup. It's going to be an expensive experiment, but whatever, that's fine. And what you'd find is that O18 is incorporated into the final product. Unusual. So what we know is true is that this reaction occurs first how you would expect. So we'll do a little bit of mechanistic work here, where the nitrile carbon, we're only going to do a partial mechanism now, acts like an electrophile, and the electrons within the carbon-magnesium bond will serve as the electrons that we're going to use for the addition. Right, so we have something that looks, I think, a little familiar. But that's not going to remove my nitrogen. If I actually just follow my arrows, and I put my lone pairs in, I get here. And this is persistent, right? So unlike with an ester, where if I did a single addition, I would have a leaving group that leaves, that remakes a carbonyl, and then that reacts again. If I added an organometallic nucleophile like a Grignard reagent to a nitrile, I get stuck here. So this is not electrophilic. And therefore it survives until the workup. Okay, so in the workup, there is a several-step mechanism that gets us to the ketone, which will actually be one of the first subjects that we discuss in SLO number 7. So for the time being, we're going to treat this as complex, I suppose. And just to give you a little bit of a foreshadow, we end up with ammonia as one of the other byproducts. That's where the nitrogen ends up going in these kinds of reactions. So the key for nitriles is to recognize that even though you're starting with a nitrogen, that you're making oxygen-containing molecules, right? And that's because of the workup. So this is a nice workaround if you have something at the C+3 oxidation level and you want to go down one level. So it's a little bit more controlled than the double additions you'd get from, say, esters. So this is in contrast to other carboxylic acid derivatives. Okay. So the other thing that I want to talk about is what happens when Grignard reagents react with carboxylic acids. Right, so we'll pick that up after a short break. Okay, so we're going to now discuss what happens when Grignard reagents, like a simple one, methyl magnesium iodide, react with carboxylic acid functional groups in particular. So these are not derivatives, they're the real thing. Carboxylic acids. Okay. So we could play the same game we've been playing. Let's find roles. So we know that the carbonyl carbon could be an electrophilic site. We know that the carbon of our methyl group could be nucleophilic. Are there any other roles that you could assign? Take a second, look at the structure of the carboxylic acid, and remember that our 4 roles are electrophile, nucleophile, acid, and base. So if you're looking at the structure carefully and you're acknowledging that there are non-electrophilic, nucleophilic roles, you might focus on this proton, right? We have something that's fairly acidic. pKa's would be around 5. One of the numbers that is helpful to have memorized. And so we have to think about, well, where will the Grignard reagent interact more quickly? At the carbonyl carbon or at the proton? So I'm basically trying to decide which of these 2 roles is faster or better inside this particular structure. So I know that this carbonyl carbon is electrophilic, but if we think about, well, what would actually impact how electrophilic, we would need to be thinking about our good friends induction and resonance. And I can see that the oxygen, not a part of the carbonyl, so this one here where I've just drawn lone pairs, this is a resonance donating substituent, so it's donating electron density to the carbonyl, and that actually makes the carbonyl carbon less electrophilic. It doesn't do anything to the acidity though. So if I look at these 2 structures, I think about, yes, something that on paper is electrophilic, but isn't that good at it, versus something that's actually quite acidic, right? And I also know that these types of structures, right, carbon-based nucleophiles, these are fairly nucleophilic species. They certainly were nucleophilic enough to react with esters. So if they're good nucleophiles, they're very likely to also be relatively strong bases. All right, so we want to make sure that we write that down. So Grignard reagents are both nucleophiles and bases. We've encountered this kind of duality before, right? Anything that's a good nucleophile can in principle also be a good base. So if I make the decision that it's going to be easier or faster for the Grignard reagent to deprotonate the carboxylic acid than actually react with the carbonyl, then what I'm going to end up with is deprotonated carbonyl, or carboxylic acid, excuse me. And let's see here, methyl is CH3, So which atom within CH3 do you think is basic? Probably the carbon, the same atom that would actually involve or be the nucleophile. So if I put a proton on CH3 where the carbon is the basic bit, I'm going to end up with CH4 or methane. And that's actually exactly what we observe, right? So this is essentially the conjugate acid of the Grignard reagent. Okay. And so we would also expect that like the magnesium and the iodine, those are likely to stay together and they'll associate ionically to the resulting O-, right? The workup here, water would be our acid, right? So the pKa of water is around 14, yeah, it is 14. So this water is actually a much, much weaker acid than the carboxylic acid. And that actually tells us something important. If we were to do this workup, this oxygen is not going to be protonated, right? This O- is not basic enough to remove a proton from water in any meaningful way. Okay, so our big takeaways here are Grignard reagents are both nucleophiles and bases. That's really, really critical. And this has an implication, which is that it would really be inappropriate for us to actually add water indirectly. We have to do our workup in the second stage. And it also allows us to make a prediction that any kind of molecule that has a relatively acidic proton won't be able to react with a Grignard reagent the way we would like. So that means that like alcohols and carboxylic acids, those functional groups will just be deprotonated by Grignard reagents rather than actually having the Grignard reagent add to a carbonyl. So a couple of words of warning in red because, you know, this is nature's way of saying danger. Carboxylic acids, in principle, could react. What we actually find is that they protonate the Grignard reagent instead of actually doing the addition chemistry that we might have wanted. Right? So this video basically shows you that nitriles and carboxylic acids have some kind of unusual outcomes. At this point, you are now able to complete the column in the carbonyl addition/reduction worksheet involving Grignard reagents, right? You've got one more column left that involves RLI, so compounds that have carbon-lithium bonds, which will be the subject of the last video, video number 5, in SLO 6.